Assalamu alaikum everyone. Today we have to start this example 8-1, which is about laminar flow in horizontal and inclined pipelines. And to solve this question we have to calculate the pressure drop in the pipeline and the head loss in the pipeline, and then we can actually calculate the volumetric flow rate of a fluid in the pipeline, having the horizontal pipeline and also in the inclined forms. So before starting this example, I will bring your attention to the equations that we use in chapter number 5, which is about the journal energy equation. So this is the equation. We can call this one as a journal energy equation, and I assume that everybody can use this equation to calculate the pressure drop or delta P in the pipeline or the head loss in the pipeline. So the first equation that we can use to calculate the head loss is this equation, the journal energy equation. The second equation that we can use, it will be equal to head loss, which it will be a function of friction factor, length of the pipeline, average velocity square, diameter, and 2g. So we can also use the head loss equation to calculate the direct value for the head loss. Now this head loss equation, it is also equal to delta P divided by rho g. So you can get this equation by generalizing or solving this journal energy equation. So this is the second equation in terms of friction factor that you can use to calculate the head loss. There are two other equations that you can also use to calculate the pressure drop in the pipeline in the form of average velocity and the volumetric flow rate. But these two equations can be only used if you are dealing with the laminar flows. Okay, so you can rearrange this equation to calculate the value for the delta P if you are provided with the average velocity, or you can calculate the value for the delta P if you are provided with the volumetric flow rate. So these two equations we already studied in the previous lectures. Okay, so this is the first part of this question, that we need to calculate the head loss in the piping system. So you can rely on any of these equations. Now to calculate this one, the friction factor, which is the second equation, the friction factor equation. Now to calculate this friction factor we have to use the Reynolds number, because the value or the equation for the friction factor, it depends on the type of flow. For example, if you are dealing with the laminar flow, the equation to calculate the friction factor, it will be 64 divided by Reynolds number. And if the value for the Reynolds number lies in the region for the turbulent flow, then we have to use this equation to calculate the value for the friction factor. Okay, now for the turbulent flow, we have to also calculate another factor, epsilon divided by d, which is the relative roughness factor. I will explain this one later, but for now what we can see, that if we are dealing with the turbulent flow, then we can use this equation to get the value for the friction factor. Also for the turbulent flow we can use this Holland equation to calculate the value for the friction factor. But what you can see here, for the turbulent flow systems we need to calculate this additional factor, epsilon by d, and epsilon by d, which is the relative roughness factor, which depends on the type of the pipeline and the material of construction of the pipeline. So let us solve this example, and the rest of the things I will explain as it comes. So consider the fully developed flow of glycerine at 40 degrees C through 70-meter long, 4 centimeter diameter horizontal circular pipe. If the flow velocity at the center line is measured to be 6 meter per second, determine the velocity profile and pressure difference across this 70-meter long section of the pipe. So we are supposed to calculate the velocity profile and the delta P within this pipeline, and also we need to calculate the useful pumping power required to maintain this flow, and we need to calculate the useful pumping power for the same useful pumping power input. Determine the percent increase of a flow rate if the pipe is inclined 15-degree downward, and the percent decrease if it is inclined 15-degree upward. The pump is located outside this pipe section. Okay, so we need to calculate the delta P, the useful pumping power, the velocity profile equation, and if there is any inclination in the pipeline, what would be the impact on the volumetric flow rate. Now to calculate this one velocity profile, the equations that we can have here, we can say this equation for the flow in the pipeline. So what we can do here, velocity profile UR, it is equal to 2 times of the average velocity multiplied by 1 minus small r square divided by capital R square. On this particular equation, the small r, it represents you the distance of the pipeline from the center of the pipeline, so it can be changed. The small r, the capital R represent you the radius of the pipeline, which is fixed, the capital R. Okay, now we have to apply some boundary conditions to simplify this equation. Now at the center of pipeline, or at the center of pipeline, we know that we can have the maximum value for the velocity, and at the surface of this pipeline we can have the minimum value for the velocity and the maximum value for the friction. So we will apply these boundary conditions. So if the value for small r is equal to 1 and the value for the capital R it is equal to 1, we will be reaching at this point of the pipeline where we can have maximum friction and zero velocity. So we can put the values in this equation. So small r and the capital R it is equal to 1 and 1. So this factor will reduce to 0, and the overall value for the velocity at this point you will get equal to 0. So what we can see from this equation, that at the edge of the pipeline we can have maximum value for the friction and we can have minimum value for the velocity. Now if we move towards the center of the pipeline, what we know that we can have the maximum velocity at the center of the pipeline. So the small r it can be reduced to 0, and the capital R it represents the radius. So this factor, the small r it will be 0 and capital R it will be 1, for example. So this factor will be reduced to 0. So the velocity profile equation, or the velocity that you will get at the center, it will be the maximum velocity. So ur can be replaced by the maximum velocity, and on the right hand side you will be getting 2 times of the average velocity. You can also rearrange this equation in this form where average velocity will be half of the maximum velocity. So we are gonna use the same equation for the velocity profile, and we will apply the same equation to this problem. On this problem, ur, which is a velocity profile, it is equal to u maximum multiplied by 1 minus small r square divided by capital R square. Now the value for the capital R square, we know it is 0.02. It is given in the question. The maximum velocity, it is given in the question that at the center of the pipeline you will be having 6 meter per second, which is the maximum velocity. So you will put the values for u max and r to get the new value for the you get the simplified equation for the velocity profile, which is asked in the question. Now to solve the other parts of the question, we need to calculate the delta P and the head loss in the piping systems. So we need to first calculate the velocity of a fluid in the pipeline. So that is equal to average velocity, which is half of the maximum velocity. So you can divide the maximum velocity with the 2 to get the value for the average velocity. Then you can actually calculate the value for the volumetric flow rate, which is equal to average velocity multiplied by the cross-sectional area. For the cross-sectional area, it is equal to pi d square by 4. So you will put the values for the average velocity and the diameter to get the value for the volumetric flow rate. Now, for the next part, we need to calculate the head loss in the system. For the head loss in the system, I told you that we can use these two equations. Either you can rely on this Bernoulli equation or you can directly use this equation. Now in this particular example, we are relying on this equation. Now if we are using this equation to calculate the head loss, we need to first calculate the value for the friction factor, length, velocity average, diameter and gravitational force. And this friction factor calculation, it depends on the Reynolds number that you get for a given problem. So first of all, we will see that what should be the value for the Reynolds number. So it is equal to rho Vd divided by mu. So the value for the Reynolds number, it comes out to be 488.9, which lies in the range for the laminar flow. So for the laminar flow, what we have seen here, that we can directly use this friction factor equation to calculate the value for the laminar flow. So you have the value for the Reynolds number 488.9, and you will use this equation to get the value for the friction factor. Now the terms in this equation have been completed. So you will put the value for friction factor, length of the pipeline, diameter of the pipeline, average velocity, gravitational force value in this equation, and the head loss equation, or the head loss value you will get here, it is 105.1 meter. Now we need to calculate the pressure drop in the pipeline. So what we can do here, we can use the Journal energy equation again here. Okay, on this equation, you can simplify this equation. If you are dealing with the same diameter pipeline, the velocity terms can be reduced to 0. There is no pump in the system, so you can remove this head for the pump. There is no turbine in the system, so you can remove the turbine part, and then you can simplify the equation to this form. Delta P, it is equal to P1 minus P2 rho G So to calculate the value for the delta P, we can use this general energy equation in this form. So in this equation, if we are dealing with the same diameter pipeline, the velocity terms will be reduced to 0, and there is no pump in the system, there is no turbine in the system. So the simplified form of this general energy equation would be delta P will be equal to rho g z2 minus z1 plus hl. Now if we are dealing with the horizontal pipeline, there is no height difference. Z2 minus z1 can be reduced to 0, and head loss we have calculated earlier. Rho and g value we will get from the question. So the value for the horizontal pipeline for the delta P, it comes out to be 1291 kilopascal. Now how we can calculate the useful pumping energy requirement? We have to go back to chapter number 5 where we did some derivations for the head for the pump calculation, and how did we relate that one with the pumping energy requirement. So head for the pump, it was equal to useful pumping energy per unit mass and the gravitational force, or in terms of power we can write this equation in the form of W dot divided by M dot G, and we can use this equation. Head for the pump is equal to W dot divided by M dot G, and we can simplify this equation in the form of useful pumping energy requirement, that is equal to M dot GH. Mass flow rate can be further written in the form of volumetric flow rate and the density, and rho GH, it represents you the delta P in the pipeline, so you can write this one in terms of delta P. So from here we can get the equation that useful pumping energy would be equal to volumetric flow rate multiplied by the delta P, or the pressure drop in the pipeline. So we have got this equation here again. Volumetric flow rate we have calculated earlier, and the delta P we just calculated here. So you will put the values here in this equation to get the value for useful pumping energy requirement, that comes out to be 4.87 kilowatt. Now this was the first part of the question. Now to deal with the second part of the question, if there is an inclination in the pipeline, then what would be the impact on volumetric flow rate? Now to solve this part, I have drawn this figure again. Now if there is an inclination angle of 15 degree, then the length of pipeline is 70 meter, and there would be a height difference here, that is z2 minus z1. Now in terms, if you use the trigonometry, this height can be written in the form of L sine theta, and then this base could be written in the form of L cos theta. Now L sine theta, you will use the equation, 70 is the length that is given, sine theta sine 15, and the value for z2 minus z1, or this height, comes out to be 18.1 meter. Now you will use this energy, you will use this delta P equation again, in which z2 minus z1, it comes out to be 18.1 meter, and head loss we calculated earlier, that is 105.1. The rest of the things you know, for the density, for the gravitational force. So the delta P calculated for a pipeline, if it is inclined upward, it comes out to be 1366 kilopascal, which is higher than the delta P for the straight pipeline. Now we need to calculate the value for the volumetric flow rate. So the equation to calculate the volumetric flow rate is the same equation that we used here. So volumetric flow rate, it will be equal to useful pumping power divided by delta P upward. So useful pumping power we calculated 4.87 kilowatt divided by delta P in the inclined form, that comes out to be 1366. So you can simplify this equation to get the value for the volumetric flow rate in the form of when the pipe is inclined upward. Now you can compare this value for the volumetric flow rate to the volumetric flow rate that we calculated for the horizontal pipeline, and then you can calculate what is a percentage increase or decrease of the volumetric flow rate in terms of inclination. So when it is inclined upward, there would be a reduction of 5.6% of the volumetric flow rate, and when it is inclined downward, you will see that there will be an increment of the volumetric flow rate compared to the horizontal pipeline. So for the second part, you can do the calculations by yourself and just try to see if you get the same percentage increase in terms of pipeline inclination in the downward direction. Okay, so this is all for example 8-1. Now to just give you some more details about this example, let us say that if we get the Reynolds number value greater than 4000, that what you're gonna do here, you have to calculate the value for the friction factor that from this equation, or this equation, which is a Holland equation. Okay, and then you can proceed the same steps that we follow in this example. Now let us see that what are the other equations, or these equations that we can use to get the value for the friction factor. Now generally there are two ways to calculate the value for the friction factor. Either we can directly use the equations to calculate the value for the friction factor, like for the laminar flow we have this equation, or for the turbulent flow we can have these two equations, or we can use the Moody's chart to get the value for the friction factor for both cases, for the laminar and also for the turbulent flow. Now let us see what we have here. This is the same equation that I have written here. If you are getting the value for the Reynolds number for the turbulent flow, we can use this equation to get the value for friction factor. Also, we can use this Holland explicit equation to get the value for the friction factor. Now, in these two equations, when we are dealing with the turbulent flow, you will see epsilon divided by d term here, and also epsilon divided by d term here. Now, this epsilon here represents you the roughness of the pipeline, and d represents you the diameter of the pipeline, and this factor here represents you the relative roughness. The friction factor is fully developed turbulent pipe flow depends on the Reynolds number and the relative roughness. So for the turbulent flow, the friction factor, it depends on the relative roughness. Now what is this epsilon value here? It represents you the roughness of the material. If you are dealing with the glass pipeline, the roughness is 0, and if you are dealing with some other materials, you can see the values for the roughness in terms of length dimension. Okay, so you have to get the value for the roughness here from this chart, and then you can divide it with the diameter of the pipeline. So this will give you the value for the relative roughness, and this term in the equation would be having no units. Okay, there will be a unit for the friction factor. There will be no unit for the friction factor, and there will be no unit for the relative roughness here. Okay. Now let's see that how we can read the Moody's chart. This one is a Moody's chart that you can use to calculate the value for the friction factor for both the laminar flow and for the turbulent flow. Okay. Now to calculate the value for this friction factor from this chart, you need to have the value for the Reynolds number, and you need to have the value for the relative roughness. Okay, relative roughness, you need to have the value for the roughness of the material and the diameter of the pipeline, and for the laminar flow you can also rely on this equation. So let's see that how we can read this chart like in detail form. Okay, so this one is an explanation. For the first part, for laminar flow, the friction factor decreases with increasing Reynolds number, and it is independent of the surface roughness. Okay, now this one is the region for the laminar flow. If there is a slight increase in the Reynolds number, you will see that there will be a reduction in the friction factor. The friction factor, it is reducing, and the friction factor is not a function of the relative roughness for the laminar flow. The second point here, the friction factor is minimum for a smooth pipe and increases with the roughness. The Coolbrooke equation in this case reduces to Prandtl equation. Now what we see here, this last line here, it represents you the smooth pipeline. Okay, now for the smooth pipeline, the friction is 0. The relative roughness that you get for the smooth pipeline, it will be equal to 0. But as you see that the relative roughness is increasing. For this one, it is 0. If you see the next line, it is 0.0001. And slightly, if you are moving upward, there will be an increase in the value for the relative roughness. So as the roughness is increasing, what we see here, there will be an increase in the friction factor. Okay, as the relative roughness is increasing, there will be an increase in the friction factor value. The third thing, the transition region from the laminar to turbulent regime is indicated by shaded area in the Moody's chart. At small relative roughness, the friction factor increases in the transition region and approaches the value for the smooth pipelines. Okay, now this represent the gray area represent you the transitional flow. So if there is a slight increase in the Reynolds number value, there will be an increase in the friction factor till you reach at the point here, which is the line for the smooth pipeline. Okay, so if you slightly increase the Reynolds number, there will be an increase in the friction factor in the transition region till you reaches a value for the smooth pipeline. Now fourth point, at very large Reynolds numbers to the right of the dashed line on the Moody's chart, the friction factor curves corresponding to the specified relative roughness curves are nearly horizontal, and thus the friction factor are independent of the Reynolds number. The flow in that region is called fully rough turbulent flow or just fully rough flow because the thickness of the viscous sublayer decreases with increasing Reynolds number and it becomes so thin that it is negligibly small compared to the surface roughness height. The Colebrooks equation in the fully rough zone reduces to von Karman equation. Okay, so what is meant by this part of the observation of the Moody's chart? If you look at the chart here, on the right hand side you can see the relative roughness, and this is the region where you can see it is a fully rough turbulent flow. So what you see here, when the Reynolds number is increasing and you are dealing with the turbulent flow, as the roughness is increasing, what you see here, there will be an increase in the friction factor value. But in this region, for the fully developed turbulent flow, you will see that these pink lines, they will become just straight. So what does it mean here? That the Reynolds number, it is increasing, but there is no impact on the friction factor, right? So in the range, in the region for the fully rough turbulent flow, what we have seen here, no matter how much Reynolds number value we can increase, but there will be no change in the friction factor value. Okay, so at a value for the very high Reynolds numbers, the friction factor will become a function of relative roughness only, and there will be no change in the friction factor values by going beyond a certain value for the Reynolds number. Okay, I'm just repeating this point. At a very large value for the Reynolds number, what we have seen here, the friction factor value, it will just become straight. Okay, you will see these straight lines. So what does it mean here? At high values for the Reynolds number, the friction factor will become a function of relative roughness. So if the relative roughness is changing, there will be a change in the friction factor value. But as long as the surface roughness or the relative roughness is same, you will be getting the same value for the friction factor. Now this is simply the explanation of this Moody's chart, but what I suggest you, that you can calculate the value for the Reynolds number by using the equation rho u d divided by mu, and then you can see that the Reynolds number value lies in the range for the laminar flow. If it is the laminar flow, you can use directly this equation, and if you are getting the value for the Reynolds number in the range for the turbulent flow, then you can use this Holland equation directly to get the precise value for the friction factor. Okay, because sometimes it becomes difficult to read this chart, and by the small variation in the values, you will not get the exact value for the friction factor. That is why I always suggest you guys to use this explicit Holland equation to get the value for the friction factor for the turbulent flows. Now let us see some of the fluid flow problems. Now here we have to deal with three things. For example, in the piping system, sometimes we need to calculate the head loss, or we need to calculate the volumetric flow rate, or we need to calculate the value for the diameter. Now these are the three explicit functions to calculate the head loss, volumetric flow rate, and diameter. If you satisfy these conditions, for example, the relative roughness lies in this range and the Reynolds number lies in this range, then you can directly use this equation to get the value for the head loss. Okay, now for example, for this head loss calculation, if you know the value for the volumetric flow rate, length, diameter, roughness of the material, kinematic viscosity, diameter, and the volumetric flow rate, keeping these conditions satisfied, you can directly use this equation to calculate the value for the head loss. Same goes for the volumetric flow rate calculation. These equations can be used if the Reynolds number is greater than 2000, and similarly you can also use the value or the equation for the diameter calculation by using this explicit function. Now these explicit functions, although you can use it directly, but from the exam point of view, I do not suggest you to use these equations. Okay, we need to see the step-by-step approach, that how you calculate the head loss using the journal energy equation or using the friction factor equation, and then you have to calculate the value for the Reynolds number. Okay, so usually from the exam point of view, we do not give you these equations, but obviously if you can remember these equations, and you can use them directly. Okay, so that could be a plus point, but we will not provide you these equations in the formula sheet. Now let us see this example 8-4, which is about determining the diameter of an air duct. So let's see what we have here. Heated air at 1 atmospheric pressure and 35 degrees C is to be transported in a 150 meter long circular plastic duct at a rate of 0.35 meter cube per second. If the head loss in the pipe is not to exceed 20 meter, determine the minimum diameter of the duct. So we need to calculate the diameter of this pipeline. The length of this pipeline is given, 150 meter, the volumetric flow rate is given. So there could be two options that we can use to calculate the diameter here. The first one, we can use the set of these four equations for the velocity, Reynolds number, friction factor and the head loss equation to get the value for the diameter, or we can use the direct explicit equation to get the value for the diameter. So we will see both of these approaches here. Now this approach in which we are using the four equations, what we can do here, we have to calculate the value for the diameter, right? So what we can do here, we can suggest some value for the diameter by ourselves in this equation, and we can get the value for the velocity. This velocity value can be used in this equation to get the value for the Reynolds number, and then this Reynolds number can be used in this equation to get the value for the friction factor. And then this friction factor can be used in this equation here again to get the value for the velocity and the diameter. And then we will see that the right hand side of the equation is balanced by the left hand side of the equation or not, right? And we can keep on suggesting or guessing the new values for the diameter until we get the balance between the right hand side of the equation and the left hand side of the equation. Okay, so for this kind of solving equations, we can use the EES system, which is the engineering equation solver system, which is not a part of your curriculum, but we can use this equation to get the values for the unknowns in these equations. So this one and these equations, they basically do the iterations. They suggest one value, they guess one value for the diameter, and they run the algorithm again and again so that the right hand side of the equation is matched with the left hand side. Okay, so you can get these kind of values for the diameter, friction factor, velocity and the Reynolds number for this problem by using the iterative approach. And the other way to get the value for the diameter directly, you can use directly this equation. Okay, you can use directly this equation. You will put the values for the epsilon, which is the roughness, head loss, volumetric flow rate, kinematic viscosity, and you will get the value for the diameter. Now here you will see that epsilon, it is equal to 0. Why? Because we are dealing here with the which kind of pipeline we are dealing with, the plastic duct pipeline we are dealing with. So for the plastic duct, what we have seen here, for the plastic duct, the roughness, it is equal to 0. Okay, that is why in this question the roughness value is equal to 0. So the diameter that we get here, it is 0.271. Okay, so this example is just for the explanation and might not be very much important from the exam point of view, but the next example in which we will show you how to do the iterations step by step to get the values for the unknown, that could be an important example from the exam point of view. Now let us start this example 8-5, which is about determining the flow rate of air in the duct. Reconsider the previous example. Now the duct length is doubled while its diameter is maintained constant. If the total head loss is to remain constant, determine the drop in the flow rate through the duct. Now we have to double the length of this pipeline, which will make this one 300 meter. The diameter, it is remained constant as that of the previous example. So the diameter that we calculated earlier, it is 0.267 or 0.271, and we need to calculate the drop in the volumetric flow rate through this duct. Okay, so if the length of this one is doubled and the head loss is kept constant, so there will be a reduction in the volumetric flow rate that we need to calculate now. Okay, so there are two options or two ways of solving this question. First one is the iterative approach, or by using the EES system, which is an engineering equation solver system. So you can have four equations, one for the velocity, the second one for the Reynolds number, the third one for the friction factor, and the last one for the head loss. Okay, now if we have the value for the, if we can guess some value for the volumetric flow rate, we can have the value for the Reynolds number, and if we have the value for the Reynolds number, we can have the value for the friction factor, and if we have the value for the friction factor in this equation, we can have the value for the velocity. And again, if we have the value for the velocity, we can multiply, we can use this equation to guess the new value for the volumetric flow rate. So the engineering equation solver, it operates the same way. It gets one value for the volumetric flow rate, and it does some iterations to get the balance between the final equation. The right hand side of the equation must be balanced with the left hand side. So by using this EES system, we got the values for the volumetric flow rate, friction factor, velocity, and the Reynolds number, and these are the values. And the drop in the volumetric flow rate, it comes out to be 0.11 meter cube per second. So this part for the EES system, it is not relevant to you, but if you know how to use this EES system, that would be fine. Okay, now let us see that what we can do from the exam point of view. So we have this equation for the head loss, right? So if we can rearrange this equation in terms of velocity, the new equation that we get here, it will be 2GdHL divided by FL, right? So if we rearrange that equation in terms of velocity, this is the new equation that we get here for the average velocity through the pipeline. Now in this equation, if we get some value for the F, we can actually get the value for the velocity. Okay, and if we get the value for the velocity, we can use this equation Reynolds number to get the value for the Reynolds number, and if we get the value for the Reynolds number, we can again get the value for the friction factor. So we are doing the iterations here again. So what we are going to do here, we have this equation and we guess some value for the friction factor. Okay, it could be any random value. Okay, what should be the range of this value? You have to go to the this one Moody's chart. So the value can be between 0.008 to 0.1. Okay, so maybe you can take any value just at the middle of this chart. Okay, so this one is the journal value. This is just simply a guess value. So we have supposed a guess value for this F to be 0.04, and then we calculated the velocity. Then once we have the value for the velocity, we calculated the value for this Reynolds number, and from this Reynolds number value, we again calculated the value for the friction factor. Okay, so we calculated the value for the Reynolds number, and then we calculated the new value for the friction factor. Now this value, it will become a new guess value, and we do the same process again. So every time you do the iteration, you will be getting the new value for the corrected friction factor. So you have to do these iterations again and again till you reach a point where the guess value and the corrected value, it will be the same. So once you have this value, once you have the same values between the guess and the corrected one, then the values for the velocity and the Reynolds number that you're getting for your problem, these can be trusted. Okay, so once you have the value for this velocity to be 4.225, you can directly put the value for the velocity in this equation to get the new value for the volumetric flow rate. Okay, so this is the approach that you can actually use in the exam, and maybe you have to do these iterations 5, 6, 7 times in the exam till you get the same value between the guess and the corrected value. Now for the same question, we are supposed to determine the drop in the flow rate. So we are supposed to calculate the volumetric flow rate. So we can actually use this equation, which is an explicit equation, directly to get the value for the volumetric flow rate. Okay, so if you use this equation directly, you have the value for the G diameter is given, the head loss is given, epsilon, which is if you are using the so you have to see the material. If you are using the plastic pipeline, so the epsilon value will be 0. You should have the value for the kinematic viscosity and the other things. Okay, so you can put all the values within this equation to get the value for the volumetric flow rate. It comes out to be 0.24 meter cube per second from this equation, and for the actual values, it could be the same 0.24. Okay, so there are 3 ways to solve the system, to solve these equations. First one, the EES system, engineering equation solver. Then you can use the iterative approach, and the third one, if you remember these explicit equations, you can also directly solve the question. Okay, so I hope you understood this example, and if you feel any difficulty you can send me an email. Okay, thank you everyone for listening.